every planet we know follows rules. Not opinions, not guesses. Rules. Rules that come from physics, from gravity, from the way solar systems are born. Planets spin because the cloud of gas they form from is already spinning. They cool down as they move away from their star. They lose their atmosphere when gravity isn't strong enough to hold it. They stabilize over time, slowly becoming predictable. That's how planets work. When a planet breaks one of these rules, scientists take notice. When it breaks two, they get nervous. But this planet doesn't break just one rule. It breaks all of them. It spins in the wrong direction against the rotation of its own system. It holds extreme heat where none should exist. Its atmosphere behaves in ways that defy long-standing models, and its position makes no sense when compared to everything around it. By every standard framework we use to understand planetary formation, this planet should not exist. And yet, it does. This is not a hypothetical object. This is not a simulation. This is not science fiction. It has been observed, measured, tracked. Its mass is known. Its orbit is known. Its temperature is known. And that's exactly what makes it disturbing. Because the more data we collect, the worse the problem becomes. Every new measurement doesn't explain it. It makes it harder to explain. The equations don't balance. The models don't converge. The assumptions break down. And at a certain point, scientists stopped asking how this planet formed. They started asking why it shouldn't be there at all. Because planets like this aren't just rare. They are incompatible with everything we think we know. If the rules are correct, this planet is impossible. If this planet exists, then something about the rules is wrong. And that leaves us with a dangerous question. Is this planet an isolated anomaly, or is it evidence that our understanding of planetary systems is fundamentally incomplete? Because if one planet can exist where it shouldn't, then the universe may be hiding far more exceptions than we are prepared for, and this planet might be the first sign that the rules we trust are not as universal as we believed. To understand why this planet is such a problem, you first need to understand how planets are supposed to behave. Solar systems don't form randomly. They begin as massive clouds of gas and dust, slowly collapsing under gravity. As that cloud collapses, it starts to spin, and everything that forms inside it inherits that same direction of rotation. That's why most planets orbit their star in the same direction. That's why most planets spin the same way. That's why, billions of years later, planetary systems still look orderly. This process has been observed countless times in our own solar system, and in thousands of others across the galaxy. It's one of the most reliable patterns in astronomy. The same logic applies to temperature. A planet closer to its star should be hotter. A planet farther away should be colder. If a planet lacks a thick atmosphere, heat should escape quickly. If gravity is weak, gases should drift away into space. These aren't assumptions. They're consequences of physics, which is why this planet immediately stood out. Based on its distance alone, it should be relatively cold. Based on its size, it should struggle to retain an atmosphere. Based on its system, it should rotate in the same direction as its neighbors. But it does none of that. Instead, it spins backwards. Its surface temperature remains extreme. Its atmosphere persists when it shouldn't. At first, scientists assumed the data was wrong. They recalibrated instruments. They repeated observations. They waited for better telescopes. The numbers didn't change. Then they assumed the planet had experienced a violent collision, a massive impact early in its history that flipped its rotation. That explanation works, sometimes, but it doesn't explain the heat. It doesn't explain the atmosphere, and it doesn't explain why the planet settled into a stable orbit afterward. So they tried another explanation. Maybe tidal forces from its star were heating it internally. Maybe chemical reactions inside its atmosphere were trapping heat. Maybe magnetic interactions were stronger than expected. Each idea solved one problem and created two more. Every explanation required additional assumptions. Every assumption made the scenario less likely. Eventually, the explanations became so complex that they stopped being explanations at all. They were patches, temporary fixes applied to a system that no longer made sense. And that's when something uncomfortable became clear. This planet wasn't just unusual. It was internally consistent, all of its strange properties aligned with each other. The rotation, the heat, the atmosphere, they weren't random. They were connected, which meant the planet wasn't broken. The model was. At some point, scientists stopped trying to fix this planet. They stopped forcing it to behave like something it clearly wasn't. Instead of asking why it broke the rules, they started asking what kind of planet could survive breaking them. And that shift changed everything. Because when you stop treating each anomaly as a separate problem, a pattern begins to emerge. The backward rotation wasn't an accident. It altered how energy moved through the system. The extreme heat wasn't Tehust, Traped. It became a permanent state. The atmosphere didn't stabilize the planet. It locked it into an extreme configuration. Each anomaly reinforced the next. What looked impossible in isolation became survivable in sequence. The planet didn't avoid catastrophe. It adapted to it. Slowly, each change arrived just fast enough to reshape the system, but not fast enough to destroy it. The planet never returned to balance. But it never collapsed either. And that's the part most models fail to capture. They assume planets either stabilize or fail. This one did neither. It endured. Once scientists recognized this, the planet stopped being a paradox. It became an example of something far more unsettling. A third category. Not stable worlds. Not failed worlds, but survivors of instability. Worlds that exist in conditions we assumed were temporary, but that, under the right sequence of events, can persist for billions of years. This planet doesn't exist because the universe made an exception. It exists because the universe allows extremes to last longer than we thought, and that realization changes how we interpret everything else we see. When astronomers detect distant planets with extreme temperatures, strange rotations, or hostile atmospheres, they often assume those worlds that they are caught in a brief phase before collapse. But this planet suggests something else. Some of those worlds may not be temporary at all. They may be locked into extreme states, enduring, persistent, and invisible to our expectations. Which means we may have been misclassifying entire categories of planets, calling them unstable when they are simply unfamiliar, calling them impossible when they are merely rare. This planet didn't break the rules. It exposed their limits. And once you accept that, the universe stops looking orderly and predictable. It starts looking tolerant. Tolerant of chaos. Tolerant of imbalance. Tolerant of worlds that exist on the edge and never fall off. This is why this planet matters. Not because it is unique, but because it may not be. And that leads to the next question. If planets like this can survive, what other kinds of worlds are we completely overlooking? In the next video, we'll look at what this planet teaches us about other worlds and why the most important discoveries may come from places we've already decided shouldn't exist.